All right, this is chapter 11, groundwater and water resources, and we are just going to be starting with groundwater flow. So we have the global water budget here. So how much fresh water is there really on Earth? So out of all the water, most of it is salty, and we have just a little bit of fresh water. And then of that fresh water, most of it is in our glaciers. 30% of it is in our groundwater, and then just the rest is on the surface. And then from that little bit of surface water, um, most of that is in fresh surface water like lakes and things. A little bit is in swamps, 11%, and then just a very tiny amount is in our rivers and streams. Water is important. We use it for almost everything. Um, and it is a renewable source. But locally, it may not be renewable. If you're living in a desert, it's going to be a long time until it rains again. And there is only so much, even though it's renewable, there is only so much water on Earth. The geologic setting affects how much is locally available and how accessible it is. As we've talked a little bit about porosity and permeability when it came up in other chapters, but here is a good look at it. So porosity is the percentage of void space in a rock or just in, like this is showing, it's not really, well, it does say sandstone, but it could just also be in sediment. It doesn't have to have been lithified and turned into a rock. Permeability is how well water flows through all those little voids. And so, really, it's kind of like how connected and how large are the voids that let water through. Here's an example of clay and shale where it has porosity, and you can see actually has quite a bit of porosity, but nothing's connected, so it has no permeability. So, these fine-grained rocks. And sedimentary layers they prevent flow. So we can call them traps or aquitards or just impermeable layers. And this is saying if it's unsorted, then you have less porosity because the little bitty tiny grains can fit into these little spaces between the big grains. If everything is well sorted and like the same size, then you have more porosity like you're seeing here, well sorted, low porosity. Oh, and yeah, igneous rocks almost have like no porosity too because they just aren't deposited like this with the holes and stuff from smaller pieces. Um, Porosity, the proportion of void space, permeability, the measure of how readily fluid can flow through a rock. Here it is on rock type. So we have shale is very low permeability and low porosity. Sandstone is higher, gravel is even higher. This is now sand versus sandstone. So this is just the deposit of sand, like at the beach, versus it having been lithified into rock. And then soil is pretty high too, gravel's high. Um, okay. Um, The subsurface water. So here are some vocab words. So we have the water table, which is pretty much like if you dig down and then you hit water, you've hit the water table. So the water table is pretty much just that surface of the groundwater aquifer. Above that, we call that saturated or the phreatic zone. And, or did I say above? Below that is the saturated or phreatic zone, and above that is the unsaturated or vadose zone. I've also heard it referred to as air sands before. Um, Soil moisture is the percentage of moisture in the soil. Um, okay. So the water table is at top of the groundwater. It's not a flat surface. It's controlled by the geology. It either typically follows the topography of the land or it can be controlled by different layers. If you have an aquitard layer, it won't be able to go on top of that. Or sometimes it can sit on top of it. You can have a perched aquifer. So it just kind of depends. Um, It flows from higher elevations to lower elevations. So just like surface waters, it's still pulled by gravity from high pressure to low pressure, but higher elevations have higher pressure because gravity is pulling on it more. The recharge area is where the rain uh, filters into the ground and discharges where it leaves the ground. And you can see the discharge areas sometimes, a lot of times here in Kentucky, like I'm in Frankfort in the Cove Springs area. All these springs are just groundwater discharge areas where you have the groundwater and then the rock, or it's been either man has like carved into it, like in our road cuts, or it just naturally is a lower lying area of topography that kind of where the rock cuts down into that water table and you get springs and then recharges the opposite of where it's raining and then coming back into. And we have better pictures of that later on in this presentation. So this is showing here where the river is cut down into that water table and it is discharging into that river and helping fill the river up. And then here is the opposite where the river is above the water table. And so it's seeping down into the ground beneath it, recharging the water table. Okay, so aquifer is a rock that has enough porosity and permeability to be used as a water source. And an aquitard means we can't use it for a water source. It's just not going to be permeable enough. So here is an Let's see. This is an unconfined aquifer, meaning that there's no aquitard involved. So you just have that vadose zone, and then you hit the water table. Here, this is a confined aquifer, meaning that this aquifer, this good sandstone here, has aquitard, so like a shale or clay layer, both above and below it, limiting it to this little area in the subsurface. This is showing an artesian well. So the groundwater has a potentiometric surface, which is if you drill a well, the height at which the water will rise to. And in this situation, you can see it would rise to pretty much the level of where the highest level that that aquifer is. And so it's a measure of water head, which is really just water pressure. All these terms, so many vocab words. Um, and so when the surface topography is beneath that potentiometric surface, it's an artesian well, meaning it naturally flows and you don't need to pump it or anything because it wants to flow up this high, but really obviously it's going to start just squirting out right here because you're not going to construct a well up into the air. You're going to let it flow. Oh, and I just explained this artesian well. Okay. Here is a map it's a contour map of the potentiometric surface of some aquifer here, and it's showing so the groundwater will always flow perpendicular to these potentiometric contour surfaces. So the direction of flow here in this aquifer is being shown by these little arrows, and it's coming in towards this Snake River. So it's actually recharging this river. Okay, so here's the definitions. Hydraulic head is potential energy in an aquifer. I think of that as pressure, but I guess it's technically energy. They're very similar, though, as far as just concept. The height of water in an unconfined aquifer reflects the hydraulic head. That's not true in the confined because it's under pressure as I just showed, because of the aquatards. Higher potentiometric surface in a confined aquifer equates to higher hydraulic head. That height it would come out at in a well. Hydraulic conductivity is a property of rock, and it's the ability of the groundwater to flow through material, and it takes into account the permeability as well as the density of the fluid. So obviously, if you're trying to like put syrup versus water through these rocks, the syrup is going to not flow as easily as the water will. So that's the difference between conductivity and permeability. And the hydraulic gradient is the difference in the hydraulic head between two areas in the aquifer. Groundwater flows from areas of high hydraulic to low hydraulic head, just like pressure systems, high to low. So here's Darcy's law. This is the equation that we use to measure discharge. And so it's conductivity times the area of the aquifer. And the area is defined as the length of the aquifer as well as the height. And the height is that change in the potentiometric surface. Um, and then discharge is the amount of water flowing past a point over a period of time. Um, and then, of course, it is influenced by the porosity and permeability because that's in this K of the hydraulic conductivity. And then it depends on the fluid type as well and how well it flows, the viscosity of the fluid. Um, Other factors in water availability. So the geometry of the host rock unit. So by that, they're talking about these perched water tables where there's this aquitard. So if it rains, you have this little perched water table right here with this tiny little unconfined aquifer. But it's not like the major water table, and you might think it is, but actually it's just this little perched aquifer. And the actual like regional water table could be much below it. But that doesn't mean people aren't like drilling here and getting the water right here. Depends on the minerals and the host rock. Some rocks dissolve easily. Some rocks might have things in them that can dissolve that we don't want in our water. Um, Locations of wells relative to recharge zones, and discharge points can all affect. Oh, and the local precipitation. Obviously, the more it rains, the higher your groundwater is going to be. The more you pump it out, the lower it's going to be. So it just depends. This is all kind of like local conditions as far as how people use groundwater. Consequences of groundwater withdrawal. So if you pump it out faster than it's recharging, you're going to lower the water table. There's this thing called cone of depression, where as you're pumping it out, it kind of sucks down. You're pumping faster than it can refill through the pores this way. So it comes down next to the well, even though it may not be that low further away from the well. That's called a cone of depression. And right here in this image, I mean, it looks very obvious, but really these things can be like very large, especially if you have a lot of wells. These little cones of depressions can interconnect. Or if you're pumping fast, like for a municipality or for a city or something, and not just the one house. Um, so this cone of depression can be just very, very big. Um, Aquifer rocks may readjust after groundwater is withdrawn. So, and that actually is happening, like where I used to live. As groundwater is being withdrawn, it it's being withdrawn not from rock, but from sediment, just this big basin fill of sediment that hasn't been lithified yet. And so as the rock is withdrawn, the grains kind of losing some of that water pressure in between the grains. So they're settling and compacting more. And so the ground surface is compacting and lowering like by like tens of feet within, I don't know, within decades. Um, Definitely within time, people can manage and like measure it and take pictures of it and stuff. And that's called subsidence. If you're by the sea, you can actually, once you take the fresh water out, there's less fresh water kind of holding the seawater back because the seawater gets into the pores too. And so then you can all of a sudden start pumping salt water out of your what used to be a freshwater well. Um, and sinkholes can develop if you're in a soluble rock like limestone. Um, if you're increasing the rate that the water's being pulled through the rock, then you're also going to be increasing the rate it's being dissolved. Um, So we use that saltwater intrusion. So it's got this little cone of depression. But if instead of bedrock underneath, you have saltwater, which is the case in your coastal zones, salt water is more dense than fresh water, so it's naturally going to be beneath the freshwater. But as you start depleting this freshwater zone, you're going to start bringing up the salt water until eventually you're going to start pumping out ocean water. And this has happened in places. And so what they do to fix that is sometimes they can go down here and they try to build a wall. Sometimes they put other wells over here to try to like put fresh water in to keep it back. So there's different things people are trying to do to fix this issue, but really it's derived from overuse of that groundwater source. Um, Impacts of urbanization on groundwater systems. So, an impermeable cover on top of your recharge area, eventually you'll deplete your aquifer. So, here is a confined aquifer where anything that rains right here is not going to get into this aquifer. And this really is the aquifer you would want because this right here could also have a whole bunch of pollution and contaminants and stuff in it. So, you'd want to drill into here, especially if it's drinking water you want, you're getting your water from here. Uh, but it's got a very narrow area to be rained on. And if you pretty much cap that with a bunch of buildings and parking lots and stuff, eventually, as you're pulling the water out, that aquifer will disappear. Um, well, I double did that. Groundwater will be handled. Okay, well, okay, did I? Groundwater recharge can be enhanced. Yes, I did. Oh well. Um, And then you can recharge artificially. Like I mentioned with the seawater, you can put in wells. Here's some pictures of some wells for artificial recharge. This is a recharge basin, just this little pond that's been built to let the water sit there. And you just kind of fill it up. Like if it's you got a really good rainy year, you fill it up and let it seep back down into the ground rather than maybe making its way to the ocean or whatever else would have happened to it. And then here's another little recharge basin. It's like they've actually treated it before there. And then some wells and recharge trenches and stuff too. All right, and then we are going to switch gears and talk about karst a little bit in the next lecture. Oh my goodness, did I not record that? Oh, I did. Good.